Hello and welcome to the session 8 of the Theory and Application of Network Coding course. In this session we will talk about connection between erasure correcting codes and network codes. So let me give you first a brief reminder of erasure correcting codes. So in such codes we start with k information symbols. So suppose those k information symbols that we denote from x1 to xk. And then what we do, we will encode them into n symbols. So those symbols, suppose we denote by y1 to yn. Then what we can do, we can send those n symbols over an unreliable channel. So this will be from the sender side. Now if you're looking at the receiver side, the receiver will get some subset of those symbols because some of those symbols can be erased. For example, here symbol number 2 and number 4 is being erased. Therefore, we only received part of the symbols. So if you have a good erasure correction code, which will revert to maximum distance separable code, MDS code, we can recover each original symbol from any k of the n symbols which are sent over the channel. So any k of the symbols of types y will be enough to decode k original symbols. So those are erasure correcting codes, and they are widely used in channel coding. They can also have a limited use in network coding, and we will show that for some simple network coding problem we can actually use those erasure correcting codes. So now let's see how erasure correcting codes can be constructed. So assume that we are working over some finite field. So since for practical use purposes we probably will use field of characteristic 2, so field that includes 2 to the m elements, then we assume that each packet that we're sending is a symbol in this field. So each packet can be represented by m bits. So now to obtain n packets that we're sending over the channel, we will multiply this vector of k original symbols by a k by n matrix, which we will call a generator matrix G. Again, in this generator matrix G, each element of this matrix is also element of this finite field GF2 to the m. So by this multiplication we will receive those n symbols that we will send over a channel, and each symbol is also element in this field. So for this matrix to have a good properties, such as MDS properties that will allow us to recover x from y, even if any n minus k symbols are missing, this matrix needs to have some MDS properties, and those MDS properties imply that any k by k minor of this matrix is a full rank. That is, if we're taking a k by n matrix, and then we're taking any k columns in this matrix, any k, so total columns, so this will form a k by k minor of this matrix. So this minors needs to be invertible. So those two conditions are equivalent. If this matrix have this property that every k by k minor is equivalent, then the resulting code will be an MDS code which allow recovery of original k packets out of any k packets that are sent over the channel and received by the receiver. We also can distinguish between a special type of code which are called systematic codes, and which this matrix, the first part of this matrix is just an identity matrix. So it can be divided in this case matrix G can be divided into two parts. First of this is identity matrix, and another is parity matrix. So any generator matrix, of course, can be written in this form by just doing Gaussian elimination. So it doesn't really change the code, but it's convenient for practical purposes, because in this case, the first k symbols that are sent over the channel are equivalent to the original symbols. So now let us discuss how to use erasure correcting codes in a networking setting. So in this setting, we have a source node S, and this node wants to communicate to the destination node T, and this is done over a network in which some of the links of this network can fail. So let's assume we have at most mu links that is failing, and in order to overcome this, we will transmit data over disjoint paths. So the number of disjoint paths will be equal to n, which is equal to k plus mu, where k is number of original symbols that we want to send. So in addition to those symbols, we will add mu parity symbols. So the total number of symbols will be equal to n, which is a k plus mu. So we'll send each of those symbols over a path, and again those paths are disjoint. So even if mu, which is n minus k paths, fail, the destination node will still receive, so it'll still might not be able to receive data over some of the paths, but it will be, because we'll be able to receive at least k packets, because even if mu failures, at least k paths will survive. Now we can use Erasure correcting codes to decode the original packets. And again, the idea here is to use Erasure correcting codes to overcome link failures. And it's done by finding enough diversity in the network using n disjoint paths, and this technique is called diversity coding. So this is a very special case of network coding, because the coding is performed solely at the source and no coding performs inside the network. As we will see in a different case of unequal capacity, we will have some additional benefit by performing coding operations inside the network as well. Now we will discuss how to use MDS codes in more general network coding settings. And we will consider a special case of h equal 2. That means that we want to deliver 2 packets to each of the terminal at each time unit. For this purpose, consider an g, 2 MDS codes, where g will be larger than the number of edges in the network. So for this code, and suppose this is a systematic code, that means basically the first 2 symbols in the code word are identical to original packets. So then we'll have P1 and P2, and then we have G minus 2 parity packets from C1 to CJ minus 2. So since this is an MDS code, so any 2 packets, any combination of 2 packets out of those G packets will be enough to decode P1 and P2. This is just a property of an MDS code, and let's see how to use this in the network. Again, we consider a special case of h is equal to 2. So we also assume the network is acyclic, and we will design a network coding algorithm using this g, 2 code. So this will be the first network coding algorithm that we will consider here. So the algorithm will run as follows. So we will visit nodes on the network in a topological order, and then for each of the nodes we will perform the following operation. So if the node of this type that only receives 1 packet, this node will just forward this, right? So if this node only has in degree 1, it will just forward this packet over the outgoing links. It will receive 2 independent packets, or more independent packet, doesn't matter, it doesn't have to receive more than 2, because for any 2 independent packets we will be able to decode the original packet, so we can do whatever we want. So once we decode those 2 original packets, we will create a new symbol that is not used before from this g, 2 MDS code, and just forward it over outgoing link. Let us demonstrate this construction over this sample network depicted in this slide. So suppose we want to send 2 packets A and B from the source node S. So what we do, we will visit nodes in topological order, and this implies that once we visit a node, all predecessors of this node already been visited. So and such order can be constructed, for example, using a depth first search algorithm. When we return from algorithms, we can assign numbers to nodes. So for example of this topological order can be, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so forth. So this topological order, of course, not unique, but once we found a topological order, we can use it for this algorithm. So any topological order will be good. So the idea is that we visit those nodes, and then once we visit those nodes, we decide on what we sent over outgoing links, and topological order ensures that once we visited a node, we already visited predecessor, so we know which packets are received over incoming links of this node. So for this network, assume that we first visited source node, then we decided to send packet P1 over this link, so I've already used this. packet P2 over second link, already use this packet, and then third link we use packets parity packet C1 because we didn't use it before. So node number 2, once we visit node number 2, is just forwards packet, so we'll just forward P1 over this. The same for 3, we just forward P2, and the same with P4, we forward C1. More interesting operation occurs when we visiting node 5. So in this node number 5, we receive two different packets. So we'll receive P1 and P2. So then we can reconstruct original packets. In this case, it's trivial because we're just receiving original packets. So then what we will do, we'll just use the next color, right? So we'll need use the next parity check packet P2. So we're sending this purple packet over those links. For node number 6, we're receiving P2 and C1. Again, the MDS property implies that by using P2 and C1, we can restore it to original packet. Once we decode it to original packet, we can use any other parity check packet. We can compute parity check packet C3, so it's yellow packet, which will be sent over this link. Again, we proceed with this algorithm. So in topological order, we assign coding and encoding coefficients according to this principle, right? So for each new edge, we use a new parity check packet from this G, 2 erasure code. Of course, if you are careful enough, you can notice that we can actually reuse colors for different links if it doesn't create a problem. But for now, just assume that we use a new packet for each edge of the network. So of course, this coding will ensure us that once we reach a terminal, so terminal will receive packets of two different colors. So it will receive two different packets from this code, two different symbols from this code, and we will be able to decode original packets P1 and P2. And this is holds for all terminals. So we conclude that by using this technique, so by using this underlying G, 2 erasure correcting code, we can construct a network code for the special case of h equal to 2. And again, the number of parity check packets that we need will depend on number of edges in the network. In the worst case, if you want to do slightly more intelligent operations, that we can try to reuse colors between different edges. For example, here on this edge, we can actually use packet C3. We can use yellow packets because it doesn't create a problem, right? So because T2 will still be able to decode original packet even if it receives C3 instead of C4. And this holds for any other terminal here. And as we saw in the previous lecture, the number of parity check packets in this case will directly determine the size of the underlying field that we need to work on, that we need to use. So the smaller the number of packets, if we're trying to reuse colors, that will reduce the parameter G of this code, and then we can use our smaller field, which is in turn will allow us to perform those operations more efficiently. So this is how we can use this erasure correcting code as a network code. So we showed a systematic code for construction of network coding for the special case of h equal to 2 using an MDS code and G, 2 MDS code. It requires relatively large field size. We can reduce the size if we reuse colors for edges or use the same symbols from the code word on edges. And this resembles coloring problem. If we're able to color edges in different colors such as to minimize the total number of colors, but still each node will be able to receive, will have incoming links of different color, then we can construct a feasible code. And actually you can see from here that the problem of minimizing the minimum field size is hard, right? So it's computationally hard or NP hard to find the minimum coloring that satisfies those properties. So finding a code which minimizes the field size is also hard. So let us see that this technique actually doesn't work for the more general case of h greater than 2. So for h less or equal to 2, we always can using underlying erasure correcting code to do it. For h greater than 2, it's not possible. For example, here in this network, h is equal to 3. So min cut here is equal to 3. So we can send 3 packets A, B, and C. And suppose we have this node V in the middle. So it receives packet P2 and P1 and P2, and we're trying to create a new symbols P3. So we know that from MDS property, if we allow to do this, and those two different symbols and this G, 3 MDS code, right? So it will be enough to use those symbols to decode those three symbols A, B, and C. However, it's clearly not possible because this node can only decode 2, because min cut between source to this node is just 2. So this shows limitation of MDS code. So in general, we will not be able to use them for more general case of h greater than 2, and therefore we need a specialized algorithm for constructing network code that will suit any network, not just case of h equal to 2.